Hello students, today we are going to discuss Unit 8 Aquaculture Farm Design and Construction from MSc Second Year Zoology. The objectives of this chapter are, so after we finish this chapter, we would come to know the design and construction of the inland and coastal pond forms and the design and construction of other aqua ponds. So to introduce this topic, the success of any aquaculture system relies on its design and construction, site physiography, source and nature of water supply, organisms to be cultured, and techniques of management, including feeding or food production and harvesting. Of the different types of aqua farms, namely land-based farms, ponds, tanks, hatcheries, raceways, etc., and open water farms like cages, racks, rafts, pens, etc., and open water farms. The success of any aquaculture system relies on its design and construction, site physiography, source and nature of water supply, organisms to be cultured, and techniques of management, including feeding or food production and harvesting. Of the different types of aqua farms, namely land-based farms, ponds, tanks, hatcheries, raceways, etc., and open water farms like cages, racks, rafts, pens, etc., and open water farms. If you look at inland and coastal pond farms, first thing what we need to see is selection of sign and site and the necessary the conditions that we need to think of. So selection of a suitable site is a prerequisite for the construction and profitability of an aqua farm. Site selection will generally be based on the species to be cultured and the technology to be employed. While selecting the site, the meteorological data relating to the mean monthly temperature, rainfall, evaporation, humidity, sunshine, and wind speed and its direction have to be studied for proper designing and construction of a farm. Next, what is the criteria for site selection? The site should have a land of optimal size. It shall be continuous and evenly leveled. The site shall have an assured water supply. Availability of potable water is a prerequisite as it is required for domestic use and cleaning also. Water and soil quality of the site shall be suitable for culture. The site shall be in an elevated area and free from floods. The site should be accessible to an assured power supply and telephonic facility. Good transport facilities and approach roads are to be facilitated. The fish or shrimp seed should be available easily and adequately in the vicinity of the site. Now, how to design and construct the hatcheries? Methods of seed production in aquaculture vary considerably with the species and the culture and the state of technology, as well as with the level of operation. For example, whether it is extensive or intensive, and the number of frequency of crops also. So, where the techniques for artificial propagation are still to be developed or perfected, or where it is feasible and economical to collect eggs, larvae, or fry from natural breeding areas, and sophisticated hatchery systems are not often used. However, even in such cases, it is generally accepted that hatchery production of seed will be necessary to stabilize and ensure regular supplies and introduce breeding techniques to raise improved seed for better growth and production. So there are different types of hatchery facilities in use. Depending on the species, locality, and investment capabilities of the aquaculturist. However, the basic requirements are about the same. There has to be the necessary facilities for holding or rearing an adequate brood stock, spawning or stripping, and fertilization of ova, incubation of fertilized ova, and rearing of the larvae to the required stage for the transfer to nurseries or other culture facilities. Then, apart from the site, we also have to look into the source and supply of water. So, the selection of a suitable site for a hatchery is very important for its successful operation. Though for various reasons it is preferable to have it located near the grow out farm, often a different site may have to be selected because of the water quality and quantity requirements. There are also cases where the hatchery forms an independent enterprise or is meant to produce seed for a number of grow out farms. In principle, surface or groundwater can be used in hatcheries if it satisfies the necessary water quality criteria. Surface water from streams, rivers, lakes, and the open sea may be relatively less expensive to utilize. However, very often there will be the need to filter the water, and where there is a high content of silt, it may be necessary to have a settling tank. Generally, sand or gravel filters with black flushing will make the water suitable for the hatchery. In salmon and trout hatcheries, stricter water quality conditions are maintained. Spring or borewell water is preferred to eliminate the risk of contamination. As far as possible, the source of water or at least the entire course of the water supply system from the intake should be under the control of the hatchery manager. Well water often has an excess of gas, which can cause gas bubble disease, but through adequate aeration before use in the hatchery, this problem can be overcome. A large reservoir of properly aerated water from a spring can be a suitable source for a controlled water supply to a hatchery. Water temperature is of special importance in a hatchery system as the maturation of the brood stock, spawning, development of fertilized ova, and growth of larvae are all directly affected by it. Spring water has often the advantage of constant temperature conditions. The temperature to be maintained in different units of the hatchery installation will depend on the requirements of the propagated species. So it may be necessary or desirable to have provisions for regulating the temperature, as for example by mixing cold and warm water from separate supply lines or by the provision of an inline heat exchanger, including a thermostatically controlled boiler, which can be bypassed if heat control is not needed. While 20 to 30 degrees centigrade is generally the temperature requirement of warm water fishes, trout and salmon hatcheries maintain a temperature between 7 and 15 degrees centigrade. In tropical shrimp hatcheries, a temperature ranging between 20 and 29 degrees centigrade is suitable. But for the majority of species, a temperature not lower than 25 degrees centigrade is considered optimal. In the giant freshwater prawn hatchery, a higher temperature of 30 to 31 degrees centigrade is recommended for better growth and survival. In oyster hatcheries, a temperature of about 29 degrees centigrade is maintained. So along with the site selection, the water supply temperature should be maintained, should be taken care. And along with that, dissolved oxygen pH also should be taken care. So dissolved oxygen and pH are other important properties of the water for hatcheries. The lowest safe level of dissolved oxygen for trout hatcheries is about 5 ppm, but a higher concentration of 7 ppm is preferred. According to Wickens, salmonoids and warm water crustacea should not be exposed to levels of dissolved oxygen below 5 mg per liter for more than a few hours. Equivalent levels for eels and carp range from 3 to 4 milligrams per liter. In other warm water species of fish and shrimp, slightly lower oxygen contents may be adequate. Oxygenation of water in a hatchery is relatively simple and is generally achieved by the manipulation of water flow from the source or the use of appropriate aerating devices. In saltwater hatcheries, maintenance of the required salinity can be important, though many species are quite tolerant of fluctuations within limits. So in order to be able to regulate salinity when required, saltwater hatcheries generally maintain supplies of fresh water as well as seawater. Then reconditioning and recirculation of water. So where the availability of good quality of water is limited, hatcheries have to resort to reconditioning and recirculation. In certain circumstances, it may also be considered necessary to reduce risks of infection by pathogens and parasites through continued use of water from external sources. When the water has to pass through a series of tanks, it has to often been the practice in hatcheries to pump the water through an aerator after it has passed through a certain number of tanks before further distribution. Naturally, there are intrinsic dangers in such simple systems of recirculation. Though oxygen can be replenished through aeration and most of the carbon dioxide dissipated, the removal of metabolic products like ammonia will involve more complex systems, which, besides re-aeration and mechanical filtration, may involve biological treatment. Recent designs of semi-closed systems employ one or more bypass treatment units, such as for denitrification, oxygenation, ozonization, etc. So, in principle, such recirculation should make it economically feasible to grow warm water species in temperature climates by reducing the cost of heating. In practice, there are many constraints to its application in commercial aquaculture, but it can be used in hatchery situations when essential. Ammonia can be removed by nitrifying bacteria. Ammonia is first converted primarily by nitrosomonas to nitrous acid, then by nitrobacter to nitric acid. The acid combines with unavailable base to form nitrates and then nitrates. Nitrates are harmless in the recirculating system. Even in prolonged exposures in culture systems, no toxic effects have been reported below 100 mg per liter nitrate nitrogen. Nitrate toxicity is influenced by water chemistry, but it has been suggested that concentrations in hard fresh water should not exceed 0.1 mg per liter nitrate nitrogen, and in seawater 1.1 mg per liter nitrate nitrogen. There are several systems and designs employed in wastewater treatment for hatchery use as well as for intensive aquaculture. The most commonly used and relatively more economic treatment would appear to be biofiltration, which may incorporate downflow filters like trickling filters, etc., upflow filters, or horizontal flow filters. Several types of filter media are in use, such as sand, gravel, oyster shells, plastics, anthracite, activated carbon, diatomaceous earth, and their combinations. Besides serving as strainers, they provide surface area for biological growth. Through biological growth and oxidation, ammonia is converted into nitrite and nitrite. The nitrate may be further combined with ions in water to form salts or reduced to nitrogen gas through a denitrification process. A rotating biofilter process is employed as a secondary treatment. So apart from cleaning the water, so biofilters also can be used for. So this is considered as the second treatment, second type of treatment. So the basic unit consists of a half cylinder tank through the ends of which a horizontal shaft is mounted. As wastewater flows through the cylinder, the discs, which are half submerged, they are rotated. A layer of microorganisms grow on the discs and act as the aerobic biochemical agent to remove the dissolved waste from the water. By arranging the discs in a series of stages, the rate of oxidation of the organic materials is increased by improved residence time. A surface area loading of 0.06 to 0.1 milliliters per day will be needed to achieve a better than 95% removal efficiency for biological oxygen demand. So decrease in nitrate nitrogen also. Then ion exchange. It is an efficient and reliable means of ammonia removal, but it is much more expensive than biological filtration. Clinoptilloid, one of the zeolites used in water treatment, is an effective natural ion exchange material for the removal of ammonia from hatchery water. It has a high selectivity for ammonia. The minimum depth of an ion exchange bed is 0.61 to 0.76 meters with a flow rate in the range 1.4 to 3.5 liters per second. Then the regeneration is achieved by passing 5 to 10% brine solution through the exchange bed with a flow of 0.68 to 1.36 liter per second per minute. Hatchery equipment. Besides the installations for an adequate supply of water of the required quality, the other general equipment required in a hatchery includes tanks for brood stock, implements for collecting and handling breeders, for stripping and fertilization, spawning tanks, where necessary, jars, troughs, tanks, or other containers, net cages or harpas, for incubating the and hatching fertilized eggs, food dispensers, larva rearing tanks, and aeration system. The brood tanks are very similar to the ones described. There are a variety of implements used for collection, handling, and transport of breeders in the hatchery. The main consideration is to avoid damage during collection and transport. In the case of large finfish, special hammocks have proved very efficient. Scoop nets are commonly used for catching broodstock for spawning. In shrimp hatcheries, circular maturation tanks of about 12 meter cube capacity made of fiberglass, or cement concrete are used. The substrate consists of a layer of gravel about 10 centimeters thick, separated from a 5 to 10 centimeter thick second layer of coral sand by a permeable synthetic cloth to prevent gravel from mixing with sand. Concentric perforated plastic pipes fitted in a PVC tube are embedded in the gravel. Water that flows into these pipes passes through the sand, preventing the accretion of waste and sediments in the sand. Water is discharged through two concentric tubes, allowing the bottom water to be drained first. Water exchange is achieved 2 or 3 times a day. Spawning tanks in the open may be built of concrete, while adequate arrangements for water circulation, as in the case of Chinese carp hatcheries. In shrimp hatcheries, indoor tanks of concrete or fiberglass are commonly used for spawning. Cylindro-conical 150 liter capacity fiberglass tanks have been found to be very convenient. The overflow passes through a concentrator provided with a 100 mesh that strains the eggs. A perforated plastic plate fitted over the conical bottom prevents the spawners from eating the accumulated eggs. Different types and designs of incubators are used for hatching fertilized eggs, ranging from improvised earthen and polyethylene jars to sophisticated batteries of jars and troughs. To a certain extent, the degree of sophistication depends on the species, the size of the eggs, and the magnitude of operations. However, the general principle involved is the provision of a regulated flow of good quality water of the required temperature for the development and hatching of fertilized eggs and prevention of infections that will affect the hatching rate. Troughs made of wood, concrete, aluminum, plastic, or fiberglass are commonly used in many types of hatcheries. The size varies, but an average size may be around about 3 meters into 0.5 meter into 0.25 meter. They are generally screened at the intake to prevent the entry of detritus and at the outflow to prevent the escape of larvae. By the use of vertically adjustable screens, the depth of water in the trough can be regulated. As an alternative, the water depth can be regulated by adjustable elbow pipes. In the case of trough-type incubators, such as the ones used in the trout and salmon hatcheries, There are egg baskets fitted in the tray. The perforations are of the shape and size to retain the eggs but allow the hatchlings to fall through to the water below in the trough. In order to allow aeration of the eggs, water is forced upward through the perforations. In oyster hatcheries, mature male and female oysters are spawned individually in battery jars containing filtered water of the required temperature, that is about 27 degrees centigrade. The spawned eggs and milk are filtered out and the ova fertilized. Larval tanks are provided for the development and hatching of the ova and for rearing through various larval stages. Different types of larval rearing troughs, tanks, and pools are in use, and some types of readily available from manufacturers also. The basic requirements are proper circulation and drainage of water to keep them well supplied with clean oxygenated water and prevent accumulation of waste products. For rearing carp larvae, circular cement pools built on the ground are commonly used. For hatching and larval rearing in Indian carp culture, meshed cloth tanks fixed on the pond bottom by means of stakes are widely used. It is common to have double tanks. The inner smaller tank with fine mesh holds the fertilized eggs for hatching. The hatched larvae fall into the outer larger cage, leaving behind the eggshells and debris. The inner cage can be removed easily after hatching. Rectangular cement cisterns with an adequate water supply and drainage are also used in many places. Let us see the design and construction of pond farms. Considering that the construction of farm facilities forms the major capital investment in pond farms and that the operational efficiency of the facilities will largely determine the success of the project, it is fully justified and necessary to devote adequate attention to their design and construction. As mentioned earlier, pond farm designers are site specific, so it is difficult to detail all possible variations. The aquaculturist will have to work closely with the design engineer to arrive at an economically acceptable design that will meet the operational requirements of the species and the culture technologies. Planned construction is feasible in most projects, except when existing undrainable ponds, tanks, or mining pits have to be used, as is the practice in some of the Southeast Asian countries. Even then, it may often be possible to design a proper form incorporating the existing water bodies for easier management. Size and shape. The size of a farm has to be determined on the basis of a number of factors, including quantity of water and extent of land available, technology to be followed, production and income required to make the enterprise economically viable, and access to markets, manpower, and equipment. Even though the design of the farm will depend on several factors, There are some basic principles which are generally followed, whether a hatchery is incorporated in the farm or not. There is usually a series of nursery ponds for growing larvae to fry stage, another series of rearing ponds to rear fry to the fingerling or yearling stage, and a final series of production or stock ponds. Many farms, particularly in tropical areas, may not have the transitional rearing ponds, and fry may be introduced directly into the stock or production ponds for grow out to marketable size. The size of ponds would vary according to the intensity of culture operations, but ranges of 0.05 to 2 hectare for nursery ponds and 0.25 to 10 hectare for production or stock ponds have been suggested. Spawning ponds could be 0.01 hectare. Smaller ponds would result in a larger area covered by embankments and water supply channels. In intensive culture systems, there is an obvious preference for smaller ponds ranging in size from 1 to 5 hectare as against 3 to 10 hectare in extensive system. As small ponds allow greater control, larger ponds take longer to fill or drain under given water conditions. This may mean, in certain situations, sizable loss of production time. Similarly, moderate sized ponds facilitate safe harvesting as too much of crowding in harvesting sumps and handling can result in fish loss. Layout of farms. The conventional classification of fish pond design into barrage ponds, contour ponds, and paddy ponds can still be used to describe the major types of pond layout. The barrage ponds are constructed in flat or gently sloping valleys or abandoned riverbeds by putting a low dam at a suitable site. It has to be built at the narrowest point to reduce construction cost. The sides of the ponds are found by the slopes of the valley, and a series of ponds can be built on the site. The source of water is a stream or river nearby. A spillway has to be built to avoid flooding of the ponds. A feeder canal from the stream will be necessary to regulate the water supply. Suitable drainage has to be provided to prevent flooding and consequent loss of stock and damage to the pond structures. Contour ponds. These are also generally located near a stream, canal, river, or reservoir and in a valley. The bottom having a slightly sloping contour. The farm is situated on one side of the valley only and floods pass through the other side. A wire diverts the water for intake through a gate to a supply canal from which each pond can be filled and drained separately. The dike should be built to carry the designed flood safely. Such a layout is possible only in sufficiently wide valleys or riverbeds. Paddy ponds. These are constructed on relatively flat areas surrounded by a dike. Such sites make it possible to use much better layout designs, including separate supply and drainage channels, seepage and pond drains, harvesting sumps, etc. Most of the sites selected for carp, tilapia, and catfish culture in freshwater and brackish water or saltwater finfish and shrimps in coastal areas would be suitable for this type of pond. Next, dike design and construction. The most important construction in a pond form are the dike system and the water control structures. The pond bottoms may or may not be excavated depending on the topography and soil conditions, but the supply and drainage channels and harvesting pits have to be excavated. Then water supply and drainage. One of the most important factors that govern the success of an aquaculture operation is proper water management. Although traditionally fish farming has been done in some areas in undrainable ponds, the ability to intensify operations will be greatly restricted in such waters. So, the adequacy of available water should be a major criterion in selecting the site. The actual quantity required for the ponds will depend on the soil and climatic conditions. But as a rule of thumb, one may calculate it at the rate of 19,000 to 20,000, 23,000 meter cube for 1 hectare pond, with an average depth of 1.5 meter, which would include an extra 25 to 50% more to compensate for evaporation and seepage. To have a more accurate assessment of the yearly water requirements, the water supply and drainage system have to be designated to convey the required quantities. Different designs have been adopted, obviously based on different criterion and requirements. In many designs, the same canals are used for feeding and drainage of water to economize on space and construction costs. In others, it is considered essential to have separate feeder or drainage canals as well as inlets and outlets. For operational safety and efficiency, it is generally considered necessary to locate the inlets and outlets on opposite sides of a pond. But in some farm designs, the inlet is located near the outlet and the harvesting sump to facilitate the supply of water to the sump when the pond is drained for harvesting. Another commonly used water control structure is the open sluice. It is especially useful for the discharge or higher than those which normal monks are capable of carrying or in catching ponds, serving two adjacent ponds to facilitate the passage of fish or fry. The closing mechanism is open sluice can be stop locks or vertical lift gates. The catfish farms in the southern USA, the most popular water regulatory system is the turn down pipe, located at the lowest point of the base of the dike. It serves as an overflow and drain pipe. The water levels can be adjusted by pivoting the pipe in order to increase or decrease the quantity of water flowing out of the pond. Besides providing a screen over the end of the pipe inside the pond to prevent loss of fish and obstruction of water flow by aquatic animals, it will be desirable to provide a special anti-seep collar around the drain pipe inside the dike to prevent water from seeping along the pipe and causing leaks. Some turn-down pipes are constructed with a double sleeve device that permits water to be drained from the bottom of the pond rather than the surface. This will rectify the main disadvantage of turn-down pipes, which is their inability to drain the bottom water, low in oxygen, and containing a higher percentage of metabolites. The size of pipe to be used should be selected on the basis of the size of the pond, the speed at which drainage has to be done, and the rate at which the pond is to be filled. The higher the diameter, of the pipe, the greater the water flow capacity. Doubling the diameter of the pipe will result in an increase of over 4 times in the water flow capacity. Generally, an 11 centimeter pipe will be adequate for small ponds of 1 to 2 hectare, but pipes of 16 to 32 centimeters are recommended for 6 to 8 hectare ponds. Now, raceway forms. The raceways are designed to provide a flow through system to enable rearing of much denser populations of animals. An abundant flow of good quality, well oxygenated water is essential to provide respiratory requirements and to flush out metabolic waste, particularly ammonia. The specific flow rate required to meet the oxygen consumption of organisms and the flushing out of metabolites can be determined on the basis of the temperature and oxygen concentration of the inflow water and the oxygen consumption and ammonia or nitrogen excretion of the organisms in the raceway. Raceways are obviously smaller in size than ponds and occupy much less space. Although earthen raceways are sometimes used, the great majority of them are made of reinforced concrete or cement blocks. Earthen raceways can be lined with plastic material to reduce loss of water through seepage. Just as for pond forms, site selection for a raceway form has to be done with special care. Naturally, the most important consideration is the water supply. The main sources of water are springs, streams, deep wells, or reservoirs. For trout, which is probably the most common species cultivated in raceways, there is generally a preference for spring water of uniform temperature. In designing a raceway, it is preferable to make use of the contour of the land. A slope of 1 to 2% is preferred so that the water flowing in at one end can be removed at the other end. Each segment of a raceway can be about 30-meter long, 2.5 to 3 meter wide at the bottom, and 1 to 1.5, 1.2 meter deep. A raceway form consists of 15 to 20 segments or more. Many of them are constructed with side slopes of 1:1 or 1:0.5. Cage forms. Design and construction of aqua farms. Holding or rearing fish in cages is a traditional practice in some Asian countries and appears to have originated almost 2 centuries ago in Cambodia, from where it spread to Indonesia and Thailand, and in recent times in a more advanced form to several other countries. Kochi summarizes the historical evolution of the concept. It was a general practice in the Great Lakes area of Cambodia to hold commercially valuable fish in bamboo cages to be sold alive. The cages were trailed in water behind a fishing boat for transport to the markets. Since this often took a long time and some of the catches were of smaller size, the fishermen began feeding them with trash fish and kitchen refuse. The fish grew well in the cages, and as a result, their market value increased considerably. This naturally led to longer term rearing of catfish in Thailand, carp in sewage fed canals in Java, that is in Indonesia, and later on yellowtail in Japan, and groupers and sea bass in Hong Kong and Singapore. Through recognition of the value of cage farms in aquaculture and the opportunities they offer for productive use of open waters, cage culture has attracted considerable research and development efforts in most parts of the world. In this picture, we can see a modern cage farms in Norway. And these are the cage farms in Norway. The hexagonal cages, how they are constructed, the framework we can see clearly. Submersible cages and cage maintenance. One of the advantages of a cage farm is that it can generally be towed away to a different location for harvesting or if unfavorable weather or other environmental conditions occur. In areas subject to typhoons or cyclones, submersible types of cages can be useful. Such cages are used in Japan for yellowtail rearing. They can withstand wind and waves much better than floating cages and can often also be used in open sea areas. The head ropes of the cages, constructed on more or less the same design as floating cages. They are attached to taut mooring ropes suspended from a plastic surface buoys. Under normal conditions, the moving ropes will be only about 2 to 5 meters from the surface, but in rough weather, the ropes are dropped to 10-meter or more. By attaching weights of about 10 kgs at each corner of the cage bottom, the shape of the cage is maintained. Additional weights may be added if the currents are too strong. The net is raised to the surface at feeding time and the feeds conveyed through the feeding passage attached to the top of the net. Under normal conditions, the moving ropes will be only about 2 to 5 centimeters from the surface, but in rough weather ropes, the ropes are dropped to 10 meters or more, attaching weights of about 10 kg at each corner of the cage bottom. The shape of the cage is maintained. Additional weights may be added if the currents are too strong. The net is raised to the surface at feeding time and the feeds conveyed through the feeding passage attached to the top of the net. A more sophisticated version of this type of cage uses variable buoyancy synthetic rubber floats that can be filled or emptied with compressed air or seawater from the surface. This is the framework of a collapsible net cage. And these are submersible cages. Two of the major problems for cage farms are fouling of cage materials, particularly nets and mesh, and susceptibility to easy poaching. Fouling makes the net heavier and prevents easy exchange of water. Anti-fouling coating, which does not harm the fish, is a solution. But the most practical way at present is a regular change of nets. Clean nets are installed at regular intervals and the old nets cleaned and dried for further use if they are sufficiently strong. Generally, the economic life of nets in cages is 2 to 3 years, depending on local conditions. Constant watch has to be kept on and deterioration in the framework and other structures of the farm. And repairs or replacements have to be in sufficient time to avoid unnecessary risks. Besides fouling, cage farms have to be protected from floating debris, rotten tree branches, and driftwood. Unless these are exceptionally heavy, no damage should be done to the strong frameworks. However, they can tear the nets sometimes, and any such damage should be repaired immediately. Even the floating booms are sometimes erected with old netting slung beneath them to protect the case. They can hinder routine operations. Next, coming to pens and enclosures. Pens and enclosures can, in some ways, to be considered as traditional structures between ponds and, transitional structures between ponds and cages. So far as environmental and stock control are concerned, while enclosures or pens continue to be used in the culture of yellowtail in Japan, milkfish in the Philippines, and salmon in Norway, attempts to introduce these systems have not met with much success in many other countries. This can probably be described to the difficulties in the use of attentive techniques, and in some cases, the right the rather high costs of embankments and water management, such as through pumping. Experience seems to indicate that the success of enclosures are for culture depends to a large extent on the hydrological conditions of the site. The design of the structures and the operational procedures have to be based on adequate knowledge of water quality, floods, waves, and currents, prevalence of predatory animals, etc. The, the screens which are removable can be located in the concrete by molded guideways. Two guideways are provided, one behind the other for each screen, to enable a duplicate to be placed in position before removal for cleaning. The screens prevent the escape of the fish stock. For proper management, these enclosures have to be relatively small, 2 to 7 hectares. Although there are much larger enclosures in Japan, measuring up to 120 hectare or more, which should strictly be called ranches or reserves rather than farms. The depth of water in different portions of the enclosure differs, and the circulation of water in the deepest parts may be insufficient to prevent the accumulation of waste and organic matter, giving rise to oxygen depletion in parts of the enclosures. Suction pumps have been used successfully for removing such accumulations, and additional flow through has been created by propellers mounted on floats. Obviously, this increases the cost of operation. This is the picture which shows that enclosed pond. This is the pump house, sliding screens, the seawater, how the water enters. Another type of enclosure or pen is the different designs of enclosures have been constructed, but generally the enclosure is formed on one side by the shore and on the other three by a wall of nylon netting hung from poles driven into the sea. In many such enclosures, concrete or stone walls are built on each side where it joins the shore to provide adequate support for the net. Around the rest of the perimeter, heavy posts of impregnated timber or concrete piles are driven into the bed, extending for about 2 meters out of the water at all times. Net barriers may be hung from steel cables strung between the poles or the concrete or steel pipes. To prevent the lateral movements of these uh, these piles, some are anchored fore and aft to large anchors blocks using strong steel cables. The nets are generally made of knotless nylon netting material. In some cases, two walls of netting are used, the outer one to protect the enclosure from floating debris and to prevent the escape of fish if the inner wall gets damaged. However, this has been found to be hindrance to free flow through of water, and now in most enclosures only one net wall is used. Though not so common as nylon nets, galvanized wire mesh or chain links are also being used as barriers. At the bottom of the poles are piling underwater. The net barrier is fixed by a rope along the seabed for about 1 meter until it terminates in a lead line. Normally, the net embeds itself in the sand or silt at the bottom, forming a good seal. As a further precaution to prevent escape of fish, heavy rubble may be piled at the bottom of the net, or in some cases, a net bottom may be provided. In planning construction, generally there is an option to use mechanical equipment or manual labor for much of the work involved. From an economic point of view, mechanical methods of construction have many advantages. The construction period can be greatly reduced. The need for recruitment and supervision of a large labor force can be minimized, and in a majority of cases, more efficient structures can be achieved. And the material that we use, or the for pond construction, we use bulldozers. So the bulldozer is probably the most versatile earth moving equipment for land freshwater farm construction, as it can be used for clearing, grubbing, stripping, excavating, diking, and leveling. However, the earth will have to be compacted to prevent erosion. The economical length of haul for a bulldozer is generally between 20 and 50 meters. Another piece of equipment especially preferred for embankment construction is a scraper, which can be used for stripping, excavating, and diking as well as compacting. The economical length of haul of a scraper is generally between 100 to 1000 meters. As a scraper does not move very easily on heavy clay, a tractor must be used to push along the cutting haul. Hydraulic power shovels and hose can be useful, particularly in excavating trenches, drainage, and feeder canals. For coastal fish farm construction, a small drainage excavator with a bucket capacity or a hydraulic excavator has been found convenient for operation and handling. A crawler tractor with a lower ground contact pressure is very suitable for trimming the soil for profile formation and also for pond bottom leveling. The main constraint is in the haulage of earth in areas where mass movement of earth is required. Multiple handling has to be resorted so as no other means of truck transportation is possible in swamps. So with this, we have come to the conclusion of or end of this chapter. So far, we have learned about inland and coastal pond forms. In that, we have understood how the selection of site should be done, what are the necessary preconditions and criteria for the site selection, soil characteristics, the topography, water source and supply. We also discussed about water quality and water quantity. We also had discussed about design of a pond farm, how to lay out the farm and what should be the size of the farm, division of the farm area. We also discussed about size, depth and shape of ponds, dike designing, pond bottom and harvesting sumps, water supply and drainage system, inlets and outlets. And we also have learned about construction of pond farm, that is methods of construction and the material that we use in construction. And apart from this, we also have discussed about design and construction of other types of aqua farms like tank and raceway farms, raceway cage farms, pens and enclosures also. Then we discussed about site and water supply, reconditioning and recirculation of water. We also had discussed about hatchery equipment and layout accessories also. Hope you all have understood. Thank you.